Hey everyone. So in calculus, we spend a lot of time talking about slope, which way a curve is headed. But what about its actual shape? What's the real difference between a gentle ramp and, say, a super steep hill? Well, that's exactly what we're diving into today. We're going to uncover the story that's hidden in the bend of a curve.
I mean, really think about it. A skateboard ramp that curves up and the top of a hill that curves down, they're completely different shapes, right? But for a moment, they could both be headed up. The first derivative tells us, yep, it's increasing, but that's it. It can't tell us how it's increasing. To really get a grip on the bend, we've got to understand the limits of the tools we're already using.
And that leads us right to our first point. We've got to go beyond just the slope. To see why we need a whole new tool in our toolkit, let's do a quick recap of what our old friend, the first derivative, can and, more importantly, can't do for us.
Look, the first derivative is awesome. It gives us that instantaneous rate of change, the slope at any single point. It tells us if we're going uphill or downhill. But that's pretty much where its job ends. It is completely silent on the character of that slope. Is it a happy curving up slope or a sad curving down one? It has no idea.
And that blind spot is precisely why we need to bring in a new character to our story. So let's meet the second derivative. This is the tool that's finally going to let us describe the bend.
So what is this thing? Well, it's pretty much exactly what it sounds like. We're just taking the derivative of the first derivative. We're doing it twice. If the first derivative tells you how fast the function is changing, the second derivative tells you how fast the slope is changing.
Let's put that another way, because that can feel a bit like a tongue twister. The second derivative is basically just asking the slope a simple question. Hey, are you getting bigger or smaller right now? Is the curve getting steeper and steeper, or is it starting to level off? That's the missing piece of the puzzle.
Now, this whole idea of how a curve bends has a fancy name. It's called concavity. Is the curve bending up or is it bending down? And the second derivative is the key to figuring this out. And trust me, this is how we analyze everything from a rocket's acceleration to the efficiency of a factory line.
Okay, this is where it all clicks into place. Look at this. A curve that's concave up literally looks like a cup. It could hold water. And what's its slope doing? It's always increasing. It might go from a big negative to a small negative to 0 to positive. It's always getting bigger. And that's the rule. Its second derivative is positive. Now flip it. Concave down is like a mound. Water would just run right off. Its slope is constantly decreasing. And you guessed it, its second derivative is negative. So here's the bottom line, the main takeaway. You don't have to guess anymore. Just calculate the second derivative, look at its sign, and you will know for sure how that curve is bending. Positive, it opens up, like a cup. Negative, it opens down, like a mound. It is that simple. All right, so a curve can bend up, or it can bend down. But what happens at that one single moment when it switches from one to the other? Well, that special point has a name, and it's our next big idea, the point of inflection. And this is where things get really interesting in the real world.
Yep, that's what it's called, a point of inflection. It's the transition zone. It's where the curve stops bending like a mound and starts bending like a cup, or the other way around. It is the exact point where the entire character of the bend just flips.
So how do you find these things? It's a really simple two-step process. First, you find all the spots where this second derivative is 0. At that point, the curve isn't bending up or down. It's kind of momentarily straight. But, and this is important, that's not enough. That just gives you a candidate. You have to do step 2. Check the sign of the second derivative on either side of that point. If it flips from negative to positive or positive to negative, then you've got one. It's confirmed. Okay, theory's cool and all, but let's see this thing in the wild. We're going to take this two-step test and go on a little inflection point investigation with a couple of functions. Our first test subject is a classic. Y equals x cubed plus x. Let's see what kind of secrets its shape is hiding. Okay, first things first, we got to find our derivatives. Pretty straightforward power rule here. The first derivative is 3x squared plus 1. Do it again, and the second derivative is just 6x. Now for step 1 of our hunt, where does that second derivative equal 0? Well, 6x equals 0 only when x is 0. So we have our suspect, a possible inflection point at x equals 0. And now for step 2, the confirmation. Let's check the signs. Pick any number less than 0, say -1. The second derivative, 6x, is negative, so the curve is concave down. Now pick a number bigger than 0, like +1. The second derivative is positive. The curve is concave up. So, did the sign change at x equals 0? Yes, it went from negative to positive. We found it. It's a true point of inflection. All right, that was a good warm-up. Now for our next one, which has a really cool little twist. We're looking at this function here. The interesting thing is that it has a stationary point, where the slope is 0, but it's not a maximum or a minimum. So let's look at the first derivative. It simplifies down to 3 times the quantity x minus 1 squared. Now that's going to equal 0 only at x equals 1, so we have a flat spot. But look at what happens on either side. Because of that square, the derivative is positive when x is less than 1, and it's also positive when x is greater than 1. So the function is going uphill, it flattens out for just a second, and then it keeps going uphill. So this leaves us with a puzzle, right? We have a stationary point, a flat spot, but it's not a peak and it's not a valley. The first derivative alone can't tell us what's going on. So what in the world is this point at x equals 1? You know it. The second derivative is here to solve the mystery for us. Let's take the derivative of our first derivative, and we get a nice simple y double prime equals 6x minus 6. Let's run our test. The second derivative is 0 right at x equals 1. Perfect. Now, let's check the signs. When x is less than 1, y double prime is negative, concave down. When x is greater than 1, y double prime is positive, concave up. The concavity changes. So that weird stationary point wasn't just a stationary point, it was a stationary point of inflection. It's where the curve flattens out at the exact same moment that it changes its bend. How cool is that? So let's wrap this all up. It boils down to this. The first derivative is all about the slope. The second derivative is all about the bend. If it's positive, think of a cup. If it's negative, think of a mound. And that one special point where the curve can't make up its mind and switches from one to the other, that's your point of inflection. And I promise you, this isn't just some abstract math concept. These inflection points show up everywhere. In economics, it might be the point of diminishing returns. In physics, a change in acceleration. These are the hidden plot twists in the story that every graph tells. So the real question is, now that you know what to look for, where are you going to spot one next?